The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people are evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. There's still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, my group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Aloha everyone, I am geologist Philip Ong, here with Mr. Dane DuPont for HawaiiTracker.com, bringing you guys another Kīlauea volcano update. Today, Tuesday, April 13th, 2021. We're now up to day 114 of this eruption, and closing in on a 4-month mark next week. And so we're going to recap the most recent information on the volcano here. It's not a whole lot of major changes, but there are some interesting changes going around along the west vent here. This is the west vent in this photograph here, showing you guys at the start. And the entry point that normally is over here at the edge of this perched rim of the lava pond has been breaking open out of its tube over and over again as a result of pressure variations in the lava coming out, presumably. So that's corresponding to some ooze-outs along the far rim. We'll show you guys some of that as well. And it seems like for the first time that I've seen, we can actually see these things acting in sync together at the same time. Like when we have the burst from the west vent, we see the burst coming up from the oozing cone. And besides that, we will go over the monitoring signals as we usually do with Kīlauea here. SO2 has been fairly stable, not a whole lot of change there, not a whole lot of change in the earthquakes. The GPS has been a little bit different, but we covered that the last week already. And otherwise, the lava lake is just slowly filling still, about 1 meter, 3 feet each week, and now coming up to it being about 226 meters or 741 feet deep. and that's below that west vent. And even though that liquid surface is rising most visibly, it's also going under all of that solid crust everywhere else in the crater and lifting that whole crust up. So before I start going through the photographs here, I just want to make sure that we thank Dane one more time for manning our chats and our streams. We'll be collecting questions, and we'll be doing questions here one point partway through, and then one more time at the end. And we will try to address the good questions that, you know, there's a lot more questions that come out of this observations that we see here than the actual details. The actual changes themselves aren't that great, but the small changes can give us bigger insights depending on how we look at them. And we might have just happened to have the camera facing the right way for once, I think. So yeah, this is that first photograph here. I'll show you guys a series of 3 photographs. These are taken by Kendra Lynn, USGS, and April 9th. So that's 4 days ago now. And I explained how this is that crusted over lava tube. The lava broke out from this west vent and flowed in that direction, and then crusted itself over, right? And that was following a whole bunch of buildup in this area with that perched pond that burst and sent its way out. That presumably there is still some other pathway that comes more this way. And we do see an exit point way over here compared to closer over here. Whereas our original exit point from the west vent was somewhere close to down in here. And this whole land has changed partly because of this island that's over here to the side. Our tilted love island, right? This was 2 months ago on Valentine's Day, that heart-shaped island that's since been rafted and attached to this levee. And somewhere in here, in this range in here, is where that original vent was. And so it might be reorganizing under the surface here as a result of these adjustments. So, but let's go back to the first of the sequence of photographs here. And this is taken about 3 p.m. on the 9th. And you see the west vent and that intact crust on the lava tube, the lava pathway that's coming from the west vent. We're now looking from the south, so it's a little easier to see it front on. Right, so that's the first of them. And then we have this burst out here. So the lava tube that's coming down through here breaks apart and breaks its crust, and the overflow is widening and deepening the channel right through here. And you can see that there's almost like a surface flow. And then there's still flow coming in here over to the side adjacent, right, through that original pathway, going through here in some way. And so this one over here is definitely on this northeast side of that west vent, related to that lava pond. This one over here is a little less certain if this maybe is a reworked route for that original west vent entry that might have got blocked and diverted somehow, or if it's part of that northeast vent complex over here. We do see the break in the lava tube in the time-lapse videos going all the way up to perhaps the base of the cone over here. So it's possible it's even coming from somewhere that's harder to see from our resolution and our perspectives here. So we'll await more information from USGS on that. And so it might be that you got to remember that this whole edifice, this whole cone of the west vent is built of spatter and tephra and chunks of lava that just fell and cooled and globbed together and hardened, and they're not very strong. It's not very coherent. It is the light material that if it gets coated in lava can be pretty buoyant in that lava lake, but if there's lava pressure inside of it, there's no reason the lava can't push its way through and out of there through some other path than the one it had taken before. So certainly the vent can be rearranging there, and when I was looking at some of the old photographs, I was recalling how tall this cone used to look, right? And the lava entry point was quite a bit lower than it is now. So as the lava lake has been rising, it's interesting to think about how it might be drowning that vent more and more and more. And so we're only seeing the entry, and the actual entry point is crusted over, but it may be getting deeper and deeper below the actual surface of the lava lake. And at that point, you are now adding that extra pressure of having to erupt beneath that cooling lava lake. And so maybe the lava might prefer to go out a slightly easier way, and especially if it can get out at a higher elevation more easily through that spatter and cinder cone, through that northeast vent, whatever configuration, whether it's that same one as from before or some new arrangement. Doesn't necessarily matter, really. It's finding its way out at a place that's a little higher up. It seems like it's easier for it to do that. So we're starting to see a little bit of adjustment there, and maybe that's got something to do with the ooze-ups that come in sync here, and we're going to get to that here shortly because I think it's pretty interesting. But that's the second one, and the final one is actually the first one I showed you guys. And by that point in time, what's happening is the lava tube, that lava channel, is crusting itself back over all through here. You'll see in a time lapse as it seems to zip itself up, cooling and crusting over, and then eventually reestablishing that margin. So you see, it seems like it breaks open and flashes open all the way up, and then it zips its way back down more slowly, and then it flashes open all the way up, and sometimes it'll go higher up, and that'll be a little detail we'll look for here shortly as well. So let's look at this compilation of time lapses that I've put together. And starting off here, this is the F1 cam view starting on April 6th, 1 week ago. And actually just after we ended our last update, in fact. This is when this video begins. And the first post we see here comes out close to that west vent, but also at the same time on that southwest wall of the crater, southwest crater wall. And you see this thing stays active and flaring for quite a while, actually. This top one up here looks like it might be something, but that's just an overflow. The pressure is filling the lava lake, and the lava lake is spilling over the edge, and that happened to be where it spilled over right there. But it's also bursting open that section over and over again. Right, so not every time that this west vent bursts open or overflows, some small flows coming over here to the side. Does it pop open? But you can see that was a big crack opening up here on this northwest side of the crater. That's really interesting, and we'll look at more detail here in slow motion. So I'm actually going to pause it right here because I'm going to talk about this in a little more detail than I did a little earlier. But it's really cool to see that at the same time as we have that pressure, we have this whole crusted over part of the lava lake. Rising lava is going beneath it, so it's clearly evident that lava is going beneath that crust, for one. It's also a little bit more clear how it actually opens, with what it looks like in a little bit more slow motion, because we see that we had that crack along the crater wall right through here, but also another crack that comes in a little bit more out over the lava itself, right? And interestingly, the lava came out this one over here, this right along the rim, rather than going through the middle of that cracked crust. And maybe this block ends up just being a wiggly piece that's just wiggling. It wasn't just the wrong shape, and it's like a loose tooth kind of thing, where the lava coming out all around it was able to wiggle it and open in that crack, or maybe it gives you an idea of how thick it might be. It's hard to say, but not too thick that you can't crack it and see the glow through there, but also not too thin where it didn't just pop open with this big flow coming out the side over here. And so interesting to look at that. Right, that's one of these loose teeth right here at the edge. That's that one. And the second one is over here, and that's this big guy. And it's really interesting. We'll see soon when I play it and a little bit faster. You'll see it looks like it pops up suddenly. So that big loose tooth also moves. So there's one and there's two right there. Right, they both move. And this one intersects the levee of the lava lake. And that causes the lake to immediately breach and start pouring out that little gap. Right? And of course, there's a lot of lava and it's got that crust, and so it essentially heals itself, it anneals itself, and stops the overflow after a little while. But still, you see the lava emerging along this crack right through here, even as this overflow eventually stabilizes. So let me put it back to the beginning here, and I'll play it from the beginning because I think it's pretty cool to see crack open here. And see, we had a first opening over here, that original crack. You almost see it in 3 distinct segments, and then that farther back one. So that one ends up being active, and this one ends up being active. And this series of 3 cracks all connects and torques this piece upwards as the lava comes out and fills this whole edge over here. So let me stop drawing on it and play it for you guys here. And a second overflow coming off the screen over here. Probably from filling lava lake as well, but not directly. So now fast, keep your eye on this thing, wiggling, popping itself back up. Yeah, you can see this one do it a little bit too. I'm going to put that one back and we'll see that popping up again. I have a little more time to show you guys this stuff. You actually see that. Both of those areas popping up together. So now zooming in on the west vent, here's that break open area, that lava tube that's breaking open, and that secondary vent that's a little further to the side. So I can see a big spillover coated this whole area. There's another flow going off in that direction. Overflows coming in at the top here. Okay, now we'll switch to the S1 camera. And the S1 camera here, we see somewhere over here is where this flash opening happens. And we're really zoomed in here, so I have to wait for USGS for better resolution imagery. There's that small little flow that comes in. So you see it bursts open and then zips back up, going in this direction. We zoom back out so we can see a bit of that ooze up on the southwest side together with these flare-ups in here. And there is that overflow happening over there. A little bit easier to see when it gets dark here. Right through there. So it goes up to, you can see in the daytime, close to the base of these cones over here. Not exactly clear what the exact spot is. So this one here, whoop, there. This part is from 2 months ago. I'm just showing you guys for comparison where the entry point was originally, and it's going to switch here. So here's our 2 months ago, and you can see clearly where it was then. It was right around here. Now it's over here to the north, a little more, and a spot right in here is, you can see close to this little nook of the entry point here. I've compiled just the nighttime parts of the S1 camera for this part of the sequence here. So you can keep an eye on these different points of glow at the top of the west vent as well. That dominant one over here on the left seems to peter out in conjunction with these ones staying open. And you can see like here we have that big burst open, but we no longer have that glowing west vent. And these things can be transient. It may not matter that much in the long term. It's something I noticed here, that we don't see this one glowing during this sequence for the most part, whereas we did last week. So this came too fast for me. Let's pull it back a little bit here. And we gotta pan it over a little bit more too. And so here's that island attached to the Levy Peninsula, and that's that section right there. And here, where this is back in March, that original entry point over here, that's a little bit more to the south, right? And that original pathway from the west vent going down this way. And so this is a more sped up time lapse here. Let me, so I can push the button. And so what you see it speed up here is that original point ends up getting shifted over to the north over here. And you don't see it as much recently in the last few weeks here, right in there. And then you see now this new pathway breaking open very close to there, right? Our original entry being right here, and this breakout path being right through here. It could possibly be that same original path, or it could also be some version of lava coming a different direction, and maybe it's coming out in multiple pathways all through here. Right? We did see it build that perched pond to the side, and maybe there's multiple pathways that can go through that rubble and head out. So those are the minor changes happening there, and interesting that we can correlate the west vent pulses at the same time as, we had that one pulse happening with the ooze-up to the southwest, and then another time we had one of those pulses corresponding to that ooze-up in the northwest that we could see with that crack opening. So interesting to see that relationship so clear for the first time. It's harder to relate it when it's all the way across that massive distance on the crusted over lava lake now, and on the far side, and it seems to be a little bit less temporally related. So interesting that the sides right next to the west vent, right, that are popping open right now, and it could just be that's the turn. That area hasn't had as many of these ooze-ups. Maybe it's just time to balance it out, that we have to have more of them over there. And in fact, there have been some more that have happened more in the northeast and on the east side since then. So maybe it's just coming up everywhere and catching up there in the west. But it is interesting to see those coming in close to the west vent, and to think about how that rising lava level may be drowning that lower down part of the lava exit point, and how that might reorganize things inside of there. There was a question that I saw earlier, came across and flashed on our quick take update, but I didn't have a chance to answer. Is could those ooze-ups on the side become exit points for the vent in the future? And it seems like if you do eventually bury all of the west vent complex in some way, where lava does have to come up through the bottom more so, right? It seems like it might have some coming through the bottom now, and certainly some coming on a higher path. But if you force more of it to be under and less of it to be above, then you can start having more of those effects where you're seeing it ooze a lot more of the volume go under and ooze up the side than maybe coming out of the spigot per se. And so it's interesting to think about that, and how that might be changing in super slow motion here. It'll probably have to, if the eruption can hang on long enough and go on for a few more months, then maybe we'll see that kind of thing happen. And so that's been most of the change there. The west vent itself has had a little bit of spatter coming out of these little holes, but not that much, not enough that it's really grown that much. So it's really mostly the same shape and size. Well, the same size, apart from collapses that have changed its shape a little bit. Mostly the same size as it's been for the last couple months here. And the last strong burst of fountaining that built the west vent was back in January, and maybe a little bit in February still. All right, so that's the time-lapse review there that goes through yesterday, and I'll switch to the USGS automatic 24-hour time-lapse generated here on their Webcam web page on the website. And so for the last 24 hours, you see that same circulation of the lava lake, not a whole lot of change in there. You see the southwest ooze-up is cooled off. You can still see its trace a little bit. You can see that northwest ooze-up is cooled off, right? Northwest over here and north over here. This is pretty close to that north vent, right in there. And you can see that since then, in the last 24 hours, you have ooze-ups over here on the southeast and northeast. So it's just maybe popping up on one side and the other side and wiggling its way up a little bit. Something like that. And looking closer at the west vent entry points, we can maybe see a little bit more convincing dual entry points now. Right? One a little bit more to the northeast, and one a little bit more to the southwest here. And this may be part of that reorganizing of the lava channel that we just saw happening here. You can see a little bit of that burst, or this particular sequence is not catching any real outbursts from this angle. But if we switch to the S1 camera, last 24 hours, same deal from the USGS Hawaiian Volcano Observatory, you do see more of this pulsing of it breaking up and then zipping back down in that area near the west vent, still ongoing within the last 24 hours a little bit. So that is most of it there as far as the interesting changes. And we'll give you guys one last look here. This is the KW camera, same as that thermal camera, but invisible. So you can see the grander picture here with the sky and the whole caldera wall all the way out here, and then the down drop block over here, and then this inner pit of Halemaʻumaʻu, all within this whole shield volcano of Kīlauea. KW camera there. All right, so just do some of the numbers here. Here's the plot for the last week, depth of the lava lake, and unfortunately we're having some returns coming off of some gas, probably giving us some false depths over here on this plot. So it's changing our scale automatic, and really the real variation is the one down over here. So it hasn't changed a whole lot. You see there's a lot of these small variations. We've been looking at that a little bit. But we are essentially at 226 meters still, 741 feet deep. And as I said earlier, still filling about 1 meter or 3 feet each week, maybe a little faster, a little slower sometimes, depending on whether you're having deflation, inflation events and how that's affecting the whole cycle as well. Right, so that's the measure of the ground tilt that gives us some proxy of some internal pressure in the volcano there. Before we turn to that, let's look at the last week here in seismic data. Very little activity here. We do see there is still ongoing activity in Pahala. We'll look at that in a little while here. But a little bit at Kīlauea Summit, small earthquakes and localized, and really a whole bunch of nothing on the East Rift. And maybe one earthquake over here, a couple down in here, but for the most part, these are all south flank adjustments and at lower levels in background than we're used to seeing here, in fact. So let me zoom it in a little bit more for you guys here. So once again, Pahala quakes, Summit quakes, and you can see that those are all clustered under the eastern part of the caldera, interestingly. And this is perhaps that area of the junction between the Summit reservoir system and the East Rift Zone. It's got some connection somewhere through there. It may not quite be through there because we suspect it might involve Kīlauea crater, which is somewhere in here, but it might be close to there. And that's the seismic for the last week. There it is in cross-section, depth, and longitude. So you see that's all fairly normal. We do see interesting kind of delineation there, right? Almost a little bit of a structure seems to be deepening to the east here. In these Pahala earthquakes, not on edge. We're only catching a piece of them over here, but that piece of it that we are seeing does seem to be showing a little bit of structure in here. It's interesting. So, in rates and depths, this one down here is interesting because now we're looking at time on this x-axis and still depth over here. The Pahala earthquakes, you can see, have been happening sporadically, sometimes a little bit more in clusters, but overall it's been average, right? There's been nothing abnormal there. So looking at that here. All right, and deformation-wise, we did have one deflation inflation event this week. It is getting a little bit bigger. We're going from +1 microradian to -3. That's a 4 microradian drop. It's not quite as big as some of the sixes that we saw earlier in eruption, but it is bigger than the last few we've had. And so to look at that more closely, let's switch here to the deformation tab and back to the SO2. The deformation tab here, here's the last 2 days, just coming out of that deflation inflation. Last week we just saw that, and really I want to focus on the last month here. So let me zoom it in so you guys can see a little better. Our scale here, you probably can't see, -8 to +4, so it's 2 microradians between the hash bars here. And we have, from about a month ago, one of our larger deflation inflation events still on the record. As you see, we went from around 0 down below -6 and came back up to, in fact, about 1, right? So we actually had a close to over 7 microradian turnaround right over here and coming out of deflation inflation event. And then we had a period that actually broke what had been a fairly consistent pattern of deflation inflation events, fairly periodic every 4 days or so, it seemed like. So we had a little bit of a longer stretch here where it goes maybe for about a week, and then we have a small one, small in the sense that it goes from maybe half microradian, 1 microradian down to 2, so 3 microradians total, 2.5, 3 microradians there. And because it's going down and coming up for a shorter distance, it's also doing it over a shorter time. And so it's a shorter time there than the time we're seeing over here. And then when the next event we saw about a week ago was slightly bigger, right? And you can see the background trend here is rising. And so we're still looking at that. It's rising, but you can see over the course of a month, it'd be rising from minus 1 microradian to positive 4 microradians. So it's something to keep an eye on, but it's nothing drastic and alarming in itself, that overall background trend. So on top of that, the second one here, and then the third one we just had is not quite as big, right, as the original one here. You see 4 different sizes, right, and we're getting closer, and whatever adjustment was happening through here, maybe it's getting back to having these bigger ones like we had about a month ago or so again. And not quite sure what that means, if it's significant. Really, it's thought to be part of the background signal here, and something to do with that denser magma having to circulate back down past the fresher, more gassy, hotter magma that's trying to come up and come out of the volcano. So it's going through some narrow part of the pathway there, and they basically have to take turns. And so you build up enough of the heavy stuff, and it says I'm taking my turn. It slides down through there, and meanwhile blocks the fresh stuff from coming up. The volcano deflates. And then once that stuff clears out, gets through, then the fresh stuff comes back up and refills and resumes to its previous action. So something like that is the best model that we've can describe, right? But some version of gas and density material movement within a volcano. And interesting to think about, coming from different depths might have different size signals, but that's something we'll need more information from USGS as they analyze that in the months and years to come here. So we're getting close to our first question break. But to finish off the signals here, this is the distance across Kīlauea summit from Wikahuna in the north to Crater Rim in the south. And you can see our scale is in meters, 0 and 5 centimeters, 10 centimeters, 15, minus 10. So we're looking at 25 centimeters total top to bottom change. And so the volcano does quite a lot of moving. Here's the buildup to the eruption over 2020 that came all the way to here, kicked it to a higher gear, right? And so most of that amount was recovered during the initial drop when the eruption began in that first week. But since then, after an initial flattish period, since then we've mostly been on a rising trend, and fairly steep too. Right? Fairly steep compared to, if you look at this one over here, right? Not as steep as this one. This was building to eruption, so we actually have an open vent. You wouldn't expect that unless it's going to open another vent. So that we haven't seen anything that steep that would lead us to believe that would be the case. But what we have seen maybe over the last 2-3 weeks now is this change in the slope of it. So it may be rising still, but which means the caldera is spreading from north to south. It's doing that at a slower rate here than it did for much of that central part of the eruption here, right? So someday when we talk about phases of this eruption, clearly there's this whole, all the precursors. There's that intrusion that happened December 2nd, and this first phase where it was all north vent and all of this adjustment, and most of the gas release happens all through there. And then the next phase is coming all this continued spreading and continued fusion and crusting over of the surface and slower output. That's essentially been drowning itself very, very slowly. And then for the last 2-3 weeks, maybe it's going to enter another phase. It's not quite clear here, right, exactly what's going on. We have seen, that's when we started seeing reports of the vent being sluggish and some of the lower SO2 values, although they've gone back up since. So it's still a big question mark what this means in the long term here, but certainly something to keep an eye on in the long term. We might look back and say, well, yeah, that transition meant blah, blah, blah. And we'll have to wait and see. All right, so one last thing here. The volcano update from USGS, just to show you guys where the data is coming from. Just reading it and rewording it and trying to simplify it. But 226 meters, 741 feet deep, and the last SO2 rate was 1,000 tons a day, April 8th. The previous one was 850, which means if we go back to the monthly measurements, our last two measurements are right in here. they're kind of in the middle in that normal range. Not as high as some of the ones we've had, not as low as some of the ones we've had, falling in the middle there. And so not any information really that is easy to extract at a glance just like that with this much information. So we are going to talk more about earthquakes after we take some questions here, but to look at the earthquakes island-wide, we are seeing not much on Kīlauea all through there. We can zoom in a little bit more and see where these earthquakes are happening. And there's Kīlauea crater. So on a closer inspection, these earthquakes are happening perhaps close to that conduit connection to the East Rift Zone, somewhere in there. And if we look at this one, that's a 1.9. It is 13 kilometers down. That is deeper than the lava conduit as we imagine, the magma conduit as we imagine it. This one, 0.4 kilometers down. That one is much shallower. So yeah, that one was within range, and minus 0.2, that one was within range too. So maybe this one is a adjustment of the deeper caldera, and this is something more to do with that connection here. So two structures, that summit caldera and then that East Rift pathway. That's putting magma into the East Rift Zone and refilling it at rates similar to prior to the 2020 eruption. Right? So, which means very slowly and with no imminent change in the prognosis of eruption. So that is it here for the first part. And well, actually, I want to back up and look at some of these Pahala earthquakes over here. So you can see that there has been action here in Pahala. 2.3, 2.1, 2.1, 1.7, 2.4, 1.8, 1.7, 2.2. All those have happened in the last 2 hours here. Right, so it does seem to be showing some activity there. And reportedly there is some tremor there as well. Mahalo for our viewers for those comments. Keeping an eye on the volcano, helping us out as well. But it's hard to connect any of that deep tremor movement with anything here on the surface, really, right? You know, there's been no temporal connection made, right? It's something to do with maybe the magma is moving through here because it's filling the area faster, right? Or moving through here, and we'll have to ask the seismologist for more information when which part of this cluster might correspond to a Mauna Loa pathway, and which part of this cluster might correspond to a Kilauea pathway. Perhaps I'm just guessing here, and presumably there's some Loihi pathway as well for these deeper earthquakes that essentially are splitting that hotspot magma generated towards the three volcanoes here. And so at its face, you might say, well, it might be because magma is still coming into Kilauea and Mauna Loa, and that's the easiest explanation. And we do see that there has been recent evidence of magma moving into Mauna Loa, and clearly evidence of magma moving to Kilauea as well. That's all we can really get out of this Pahala earthquakes. And with that, Dane, we will start saying some thank yous.
All right, well, let's get into it. Do want to thank all of our viewers that were able to jump in today. If you haven't yet, make sure to like, subscribe, share this video. We don't have an advertising budget. We really rely on people like you to get that get the information out there. If you appreciate this type of content, sharing it really helps. Also consider making yourself a member on hawaiitracker.com. That's where we post to primarily to archive all of our work, and you can jump on there and find out what's new and what's different, and get a variety of posts from video updates to text updates. We're doing a lot of different things there. And third is monetary donations. We do have a couple of monetary donations. I do want to shout out Stuart Fisher, and the other one was Lisa J. Really appreciate those. So yes. Also want to thank our sponsors. Get through it real quick. We are sponsored by Kaleo's Bar and Grill in the heart of Pahoa. Some fine cuisine, always something special in there. Indoor, outdoor dining. You know, really good staff, take care of you. It's one of the best places in Pahoa. to grab some grinds. Also affordable. Competitively priced. It's not going to break the bank going. So really good quality. Can't vouch for it enough right there. Secondly, we are brought to you by Kalani Tours out of Kona. They do some different types of tours, primarily focusing on they have a deluxe volcano tour now that involves the nighttime viewing of the lava lake and dinner in Volcano. So they have that whole package, and they really focus on the small kind tours as opposed to the giant tour bus kind tours. So if that sounds appealing, you're coming out here, check them out. And with that, let's get into some questions, huh? What do you think?
All right.
So we got a few here. Since we're just talking seismology, let's talk about it a little longer. So there's one specific quake that Jennifer on Facebook was asking about in the Pahala region. It's the little one that's down by South Point. It's like a magnitude
2.1?
2.1. Yeah, that one at 42.1 km.
Yeah, it's pretty deep down there. Yeah.
Yeah, and also seems like it's outside of what we would consider the deep quake area in some regards. She's just wondering if you had any ideas about that or comments about that.
The whole volcano Mauna Loa sits on top of that old ocean crust, and I would imagine it's essentially that kind of settling earthquake that we've described before, right? There's all kinds of movement happening on Mauna Loa and through in that magma generation zone, and so one little adjustment off to the side is reasonable. If there was a whole, giant swarm of earthquakes coming from right there, that might be something a little bit different. It might be, you have to examine them in more detail, right? You could have a bigger one with aftershocks, or you could have a lot of small ones that that's what we look for something more volcanic in nature. It would be lots of small ones rather than several big ones, right?
Mm-hmm.
And a tremor, and right. And it is noteworthy to say that there is tremor. There has always been tremor from some of these Pahala earthquakes for a long time, right? And a lot of them have been a long period, and I do realize that it does change. It's interesting to note that change here, but I'm not really sure without asking more from USGS seismologists. If there's anything else we can say about that, really?
Last time we did do that about Pahala was kind of not really. It's kind of a wild card out there.
Right.
So the next one is from Richard on YouTube, and I'm changing it a little bit, but he's asking about seismic activity downslope from the caldera. Perhaps those 3 earthquakes that you were showing. He's asking about, is that suggesting magma movement or anything along those lines?
No, we're not seeing anything that looks like magma movement. I mean, it could be that. I mean, the volume moving between the summit and the east rift zone has been changing, and so that's what I imagine that these 3 ones are some adjustment of that, right? It's some adjustment of that pathway. Maybe a little bit more is trying to get to the rift zone, and it needs to widen the pathway a little bit, and it does that by shoving its way in there, and then you might have a couple of earthquakes as a result, right? Or more than a couple of earthquakes, in fact. And the caldera might need to adjust because of that moving material, and so that's all fairly normal there. Further on, if I'll scan down the rift zone here, really don't see anything coming up. This one's a still south flank over here. Not very deep, but still qualifies. There's that long Pahoa flow. Keep going over here. There's one kind of under Kīlauea area, but not really on a rift zone either, and similar kind of within that range of south flank. So really I don't see anything anywhere even on the rift zone now that I look more closely. It all seems to be south flank.
All right. So next one is still going to be related to the earthquakes, a little bit more general this time. Casey Tanner asks, if you made a 3D model of all the earthquakes on Kīlauea Mauna Loa for a year, would you be able to model the pathways? You want to comment on that a little bit on like
Yeah,
the
yeah.
modeling
So
process?
we don't have a 3D model. We have a 2D model of those
Hmm.
pathways. In fact, maybe I can dig it up to show you guys. Maybe not right now, but maybe the next time I'll dig
Yeah.
that up and pull it out, put it in the queue. But we do have that, right? I've shown it a little bit in the past, but that shows you
That's
the
basically. Go ahead.
edges
Sorry.
of the pathways, and it's hard to see beyond the edges to the middle. Is kind of what you get. But you do get an idea of the cloud of where they are and what shapes and directions for sure. Yeah.
Right. Basically, they do that. It's just we don't have the 3D grand scale, interactive
Yeah.
version of it
We
yet.
just don't have it plotted that
Um,
way yet, and there's no reason why
yeah,
we couldn't. It's just no one's done it.
time and money.
Yeah, at least that I've seen publicly available for us to find easily here. And yeah, that could be an interesting pit project someday if we could fund it there. Yeah, and get an
Right.
intern.
There we go. UHH students, let's go. We do have a donation from Richard L. Thank you for that. We just answered his question. So taking that and transitioning a little bit. Oh, I had one lined up. So, oh, okay. In relation to that, has there been any information that we've heard of recently to suggest changes to the magma reservoir in terms of our rate of resupply? Do we know if it's anything recent about that?
It can be calculated, just like there have been calculations that are presented on the supply of magma into the Kilauea summit and its rift zone and deep rift from movement in the south flank and into Mauna Loa. You could calculate that for Kilauea, but I haven't seen that information publicly and how that compares to the previous trends that we were on, right? So we'll probably have to wait to see that, but possibly, the people who have these models can run rough preliminary models and get some preliminary results, and you might want to be more careful and double check everything before you publish it. And that's one of the things that USGS always does is check everything before they publish it, and that may be why we don't have that at this point.
Right. Well, that appears to be it for the majority of the questions. There is one here. If you want to just finish up on this one, Michael T asks about another volcano on a different island in Hawaii, asking about Diamond Head. Could that erupt again?
Yeah. So I really out on a limb here. Those guys that are on campus not far from there are the ones to really be asking about this, right? But in theory, geologically, the fact that there has been a rejuvenated eruption there indicates that there could be another one at some point. Yes, it's highly unlikely. It wouldn't be very frequent in time, right? So the chance of a human actually experiencing that would be very small. Any particular human, right? But over the long term, maybe all humans might experience it at some point. We're around long enough, right? And not just from Diamond Head necessarily. I don't know about that exact area, but other areas nearby or even offshore. Right, there have been lots of submarine vents, and that'll be something to dive into and present to you guys some other time. Down the road there, yeah. But yeah, because it's happened before, fairly recently geologically, it seems possible that it could happen again. But I don't. That's just a very vague general answer without knowing any specifics.
Right. Well, that does it for me on the question end at this point. So I will pass it back to you.
All right, mahalo, Dane. So we're going to talk a little bit more about these seismic data, right? But we're going to do it focus on two different publications here. One is just this shorter volcano watch that we promised we'd cover last week, and it's what's that seismic noise, right? So what we're showing today is the seismic plots that are called spectrograms, and these spectrograms are showing So normally you would just have on the bottom, you have time going this way. And so this is over a course of a few minutes here. 12:39 on April the 1st. It's showing 12:43 over here. And normally you just have your signal, and it might go up or down or something like that, right? So what they've done is take it from one signal and plotted it across all different frequencies. So now on our y-axis we have frequency of the signal, and it's colored by the intensity on that frequency. So the brighter the color, then if you'd imagine in 3D, like this top line here would be not a whole lot, not a whole lot, not some little wiggles, and then some more noise in here. You're seeing it change color right through there, right? That's kind of how it would look for one individual. If you had at this high frequency, we're looking at just that particular band. That's normally what you're seeing is something along those lines. So they're pointing out here, this whole article is about all the different kinds of noise that you might have. And this first one here is a station steam crack near Pu'o'o on Kīlauea's East Rift Zone. And because it's showing only on these higher frequencies, it's a giveaway that it's a rain signal here. And so they've superimposed here what that rainstorm signal looks like on a spectrogram. So this is clearly something, once you have a new way to plot your data, which is more useful, then you have to have a specialist to read the graph as well. And this is a good lesson here from the experts at HVO here, right? So they say they actually record the approaching rainstorm just after 12:40 p.m. And so they can have persistent signals. They can check on the webcams to see if there's rain in the area, and then kind of corroborate their interpretation based on that. So just to show the rain can have an effect, not just on things like the tilt meters, but also on these seismic signals, and given away by coming in at these higher frequencies there. So the next one here is showing a couple of things together. The more interesting one is what looks like these worm tracks at the top of the signal here. And these are actually, as you can read already, maybe, or maybe you can't, helicopter signals. And so helicopters are as they come toward or away from the station, the frequency is a little bit different, right? And closer and farther, the frequency varies. And so you see two helicopters flying here, apparently, or maybe it's one and it's just having some kind of split signal. Yeah, I'm not quite clear about that. Maybe it's just one. Interesting there. Maybe someone can chime in if they know the answer in our audience there. But they're a transient man-made signal, whereas in the bottom we have this eruptive tremor signal that comes in at these low frequencies. So down here, frequency between 2 and 6 hertz is where you're seeing this ongoing tremor. So this is a station at the summit near Halemaʻumaʻu, and it's picking up both the tremor, which is what you're looking for, but then you also have, fortunately, superimposed noise on a station at different frequencies, right? And this is a great example of why you might want to use this kind of plot rather than your typical wiggle graph, right? Because if you're using your typical interface, you might just see it. Oh, okay, there's some tremor, there's some tremor, there's some tremor. Oh, the tremor got a lot more. Tremor got a lot more. You can't break apart whether it's just that low tremor or whether it's a helicopter flying by. It actually would combine the signal there. So that's why you want to look at something like a spectrogram to be able to clearly pick out what you're looking for and separate it from what you're not very easily visually here. Right? That's really one of the great examples. This next one here is showing different kinds of earthquakes. So when you have earthquakes that are local, they show up across all their frequencies, top to bottom. And because this is time on the x-axis here, at one moment in time they occur. So there's one earthquake, and another 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 one over here, right? And this is on Mauna Loa's southwest rift zone, this particular station, back from about a month ago in March. But on top of that, you can see coming in at this low frequency, 2 hertz and less, lasting a long time, kind of waning out, coming in strong, and then degrading over time. That's your typical signal for a teleseism or a distant earthquake, right? That, in fact, is the magnitude 7 that struck Japan last month near Ishinomaki, as it states here in the Volcano Watch article. So interesting to see that looks like there, and another good reason to be able to differentiate. And it shows you the value of these kind of flats. And so this one over here is something different. We're talking about a rockfall in this case, where it's coming in across all the frequencies strong, and then it's deteriorating across the lower frequencies first before the whole thing degrades as well. Right? That's the layman's version of what's more elegantly written here in this Volcano Watch. But that's what they're saying here. One trick seismologists use to identify rockfalls is to look for the slight decrease in low frequency content as the event progresses. So the majority of recent rockfalls observed by HVO seismologists have been on Pu'o'o, some of which have been preceded by helicopters flying near, or perhaps even into the cinder cone that's written in here. Right? So perhaps any of the vibration from the helicopters could be triggering some rockfalls, is I think what they're trying to say there. Right? It's interesting that they could, if they see a helicopter signal and then they see a rockfall signal as well. So that's interesting things you can see besides just volcanic activity on the spectrograms and the seismic signals here. It does note, there have been documentation of hurricanes, whale songs, football games, and nuclear testing in different ways, right? Here in Hawaii, weather, local air traffic, eruptive tremor, and rockfalls are a few of the interesting seismic signals that they can see. So I just wanted to go into a little more detail there in case some of you guys are interested to know a little bit more about the earthquake signals here and what they might mean. Yeah. And the second part of this little concluding piece here is an article Dane shared last week as well, written by Roman, Soldati, Dingwell, Upton, and Shiro, and earthquakes indicated magma viscosity during Kilauea's 2018 eruption. So this was just published in Nature. It's available for free view online. Find a link on hawaiitracker.com. And essentially what they're doing is looking at, let me zoom into this figure here. You're looking at the direction of how to put this simply, right? They're trying to show you guys what the direction of the primary stresses, the pressures are that earthquake is relieving, right? So every earthquake, based on the signals that it expresses across all the seismic stations, you can see, well, it was probably something that was this shape of this size and moved about this much to generate that kind of signal seen at these stations, these distances away from them. That's kind of how it goes. So what they've identified is that there were a subset of these earthquakes that occurred, drawn in red here, with directions that, rather than being consistent with the previous magma movement, had rotated by 90 degrees essentially, right? I'm not saying this very well. Maybe I can come back here to the abstract and find the key sentence for you guys here. Rotated fault plane solutions and earthquake swarms at Kilauea and other volcanoes might provide an early indication that magma of heightened viscosity is involved. So this is what they're getting at, is that there are certain times, and maybe I'll move down here to show you guys, we'll come back to that one. Show you guys this plot to start here first, right? This double plot, this is maybe the more important one. So this is longitude in the bottom. So you basically have a summit over here, over here, and over here is a lower east rift, right? So you actually have plotted in little blue dots over time. This is 30th of April going to mid-June, continuing over here from mid-June to the end of December. And you have the summit collapse sequence in blue all through here. And you have, it's hard to see, but you have plotted the earthquakes that accompany the beginning and opening of the rifts on the lower east rift zone down through here. Right? And so that's what these earthquakes are a subset of. And they've plotted on here the solutions and highlighted in red which ones are the ones that have rotated fault plane solutions as an indication of denser magma viscosity. Right? So what they're saying is that there is denser magma involved as initial fissures opened up in the lower east rift zone. Fissure 2 and 3 here is around this time. You're seeing it around a fissure 16 through 19 time as well, on that most part of the rift zone as well. And then you don't see, you see it one more time here in the upper lower east rift zone, kind of in mid-May. That's an interesting one right in there. But otherwise, a long gap, and none of them all the way until you get to when the eruption, when lava stops coming out of Ahu'aila'au, fissure 8. And the magma is rearranging itself back underground at that point in time. And so you do see a cluster of them as essentially the magma from the summit stops pushing into the area. And so all the magma, the older magma that was in the area that had been shoved aside, was able to settle back into that area. And likely it was that settling back that squeezed lava out of fissure 8 and Ahu'aila'au that last little burp that occurred in those first few days of September, right through here. Right, that might have been part of that adjustment too, of some of that still the younger lava, right? That's shallower down, right? Not as far below the surface, but everything's moving underneath it, so it can get popped and pushed and get squirted out a little bit more too. That's one possibility of what happens there. So I'll come back up to this earlier plot here, and this is just showing fissure 8 is right here, and all these high viscosity magmas are all shown to be downrift, right, on those fissures that were shown to be exhibiting more strombolian activity and showing higher viscosity magmas from the lava chemistry as well. So that does all tie together. It's interesting to see that there. So that is most of it there. The reason that this is happening is because they're finding there's a threshold in a bulk viscosity across which that fault plane rotation is happening. So that's why they're confident in tying this to the magma viscosity, is because of this relationship that they found. They go into detail in the paper as well. So, but I won't go into that here in our recap of it. Just to show you guys how, by looking at these signals during the eruption itself, we're able to see signals of these denser magmas, right? If you look back at this plot, you're not really seeing anything happen here before vents are opening on May 3rd. You're not really seeing a whole lot. Well, actually down here, this is Pu'u'u vent. And Pu'u'u vent, yeah, this is the, sorry, I forgot to talk about Pu'u'u vent. There are May 1st, May 2nd up here. You do see a series of migrating east movement of these possible more viscous magmas, right? And they actually talk about there might have been some semi-solid plug over there. The magma has been flowing through Pu'u'u for so long, and you do have cooling happening there that maybe you essentially cooled off that part of the rift zone that went further down rift, and that's what had to get pushed aside and failed. And they're saying maybe they could see the signals of that happening here in the early days of May. Right, so at that point in time, on May 1st, you might have been able to say, okay, the barrier below Pu'u'u is giving way, but we also had other signals, right? We had the April 30th collapse, and we had the earthquakes and other things as well. So not just the directions of them, right? But so I have seen some of the headlines made that this maybe could be predictive. And maybe so in other places, like if you have a place like Iceland where you might have either kind of magma coming up, and you want to know if the magma primarily is one kind or the other, that might be more useful. Maybe on other volcanoes in Hawaii that have different characteristics, like maybe Hualalai might show something interesting in that regard. But the thing on Kīlauea and Mauna Loa is that we see this pattern pretty common, that we quite often have the first phases of the eruption always clearing out whatever magma was in that pathway previously, whether it's down in the lower east rift zone or at the caldera. You quite often have mixing of magmas and contamination and evolution of magmas over an eruption, such that you can flush that stuff out every time and then replace it with the fresher stuff every time you see that pattern. So just because you see this at the beginning doesn't necessarily mean that you're going to have an eruption that's going to have this kind of magma. It just shows that it's moving around, which is something that we know happens just about every time. But it's still very, very useful, and in a place where you don't really know what kind of magma it is to start with, unlike Hawaii, like Iceland, where you have volcanoes in close proximity of different magma compositions, then maybe that's really a tremendous asset there. Right? And so that's the big picture looking worldwide more so than Hawaii, as the predictability of it that way. So I do want to point out a couple more things. On Hawaii Tracker, there is a video Dane posted, the difference between volcanic hazards and risk from Iris there, so you guys can go check that out. It's a short little video there, but interesting if you guys want to get into that, right? What's the actual hazard, what's the actual risk? And then I'm going to show you guys some of the photographs that have been coming through Hawaii Tracker recently as well. So this one here is from Angela Starr, April 11th. Kau Kamaka photography. You can see the glow from the summit here. Mauna Loa in the background. Looks like some planets in the sky here, perhaps. Can't quite tell. We'll move on to Stephen Davies. Starry, fiery night here. Fantastic. Looks like you can see Pu'upuai here in the foreground with the glow from Kilauea Caldera behind with the amazing stars, of course, as well. We have Harry Dorgan, Heart of Gold. You can see from Kau Desert, April 8th. Fantastic exposure here on the stars. And you can see big gas cloud coming from Kilauea with a illumination of the glowing lake there. Fantastic stuff still. From Harry, that's one, and we'll show one more from Harry here. Primal Forces from Kilauea Overlook. It's looking now from the north back to the south. The inner pit glowing. And starry sky behind there. That's the ones from Facebook, and of course we do encourage photographers to post on hawaiitracker.com directly, as Cody has done here. And fantastic image here of brightly glowing Halemaʻumaʻu and the Milky Way rising here. And this is one, if you go on hawaiitracker.com, you can click and buy the print right just like that. So good thing to go check out there. And one last one, just moving off Kilauea very briefly. There are some great photos from Hualalai by Andrew Hara, Hawaii Tracker as well, showing some of the different summit creators up there. So I'll check that out if you guys want to see more on that. And I believe, Dane, that we will, that pretty much does it for us there.
All right, well, let's do one last round of questions. If anybody does have any questions, let's throw them into the chat, and we will try and get them in the queue. Let's go back first to the volcano watch on the seismographs and the different signals that you can see in there. And the one that's interesting to me, it was not really mentioned in there, was the Puhakaloa training signals. Right, because those are well-known signals, and USGS handles them, without issue. It seems I never see like false positives where, oh, there's a bunch of earthquakes happening. Oh, it's never mind. It's a munitions cluster. No. They seem to have that cleared out. So I was looking for an example. I couldn't find one. All I was able to find was a assessment by the Defense Threat Reduction Agency in 2006 that was saying that basically that from USGS the azimuths are known for where the source of the fire exercise would come from, and they always happen in clusters at irregular speeds and different arrivals, but they tend to have a fairly high frequency, and they create a more consistent, more recognizable signature. That was just one interesting thing to me that we know that they have to deal with. But yeah, it gets ignored a lot of the time.
Yeah, that's really not, when people are nearby and they hear the sounds, they want to know what's going on. That's what really the only time we look for those. Otherwise, there's really not a whole lot of interest in those, and it's easy enough to tell the difference that even the computers can do it. Right, so it's a different profile entirely in how it comes into the signal. Even with a one band only, you can tell, and it's even easier with a broadband there, right?
Right. All right. Yeah. So Dorothy asks, it's not very sturdy if the helicopters can cause the rocks to fall, huh?
Yeah, not at all, right? We've seen that some of those signals of that area, the instruments literally fall into the hole, and you see the solar panel is getting torqued as their mounts are falling in or hanging off the edge. So yeah, it's super unstable up there for sure.
All right. We have a $5 super chat from Michael T, who asks, how can an eruption go from a lava overflow to plume and back to lava like Mount Etna did?
Okay, so the question is more about Etna, right? So I mean, Etna's magma is stickier than Hawaii's. It's more viscous, and that allows the magma to essentially trap the gas a little better than the Kīlauea. On Kīlauea, the gas just bubbles out all the time. It's been a while since we've said this, so it's worth saying it again. On Etna, the magma is just slightly stickier, so it can get flung out pretty easily, but it also holds on a little bit longer than our magma, to the point where it can build a little bit more pressure, to the point where it's more episodic for one, but also it can fountain way higher than our fountains, because it's got that built up pressure that it is venting off, right? So it's their paroxysms, as they call it in Etna, can they're an animal all of their own. It can involve both overflows and of lava coming up, as a big slug of gas is pushing up lava that's maybe less gassy and then overflowing it, and then otherwise you're releasing some other built up pocket of gas that's just jetting. That's the best I can
I think you
try
got
to
it.
simplify it there. Yeah,
I think you got it. We have a $9.99 super chat from Dorothy. Just says thank you. Mahalo for that. Mahalo Michael as well for asking the question. We do have a €5 super chat from Stuart that asked a question in one of our premieres. I just want to address that one. Hopefully he's here. But he says, if Kilauea is affected by changes in the polar shift within the Earth.
I'm not quite sure what he means by the polar shift in the Earth, right? I mean, we do know that the magnetic pole moves,
right?
If that's what he's talking about, and it's moving at, it's at a fairly slow rate, not to the point, not fast enough that it's changing during this eruption substantially, right? For example.
Mm-hmm.
So normally the only thing that changes is that the lava itself does have a lot of iron in it, and the iron is in long. It's structurally like it's in a long kind of mineral, so that it's like a little compass needle. You can have the iron within the cooling lava flow aligned to the magnetism of the Earth at the time that flow is cooling. Right, so every lava flow that flows actually imprints itself the magnetism at the time that it's flowing. So you can, over time, see the change in magnetism by looking at a change in the magnetism within lava flows, and that's a large part of how we've got our whole magnet, or how the proper way to describe it now, right? Our magnetic timeline, right? Or that shows the normal and reverse periods, especially because there are times when a pole flips from north to south, and maybe during that transition time, if that's happening, that's something shorter term that might be manifest differently in Hawaiian volcanoes, right? But overall, that magnetism is generated by that circulation of that outer core liquid iron, which is at a much deeper area than the magma moving through the volcano. So there is a long chain of dominoes that connects them, so to speak, but not to the point where a change in that circulating iron should change anything with um, the actual hotspot and the magma pathways from the hotspot to each volcano and each volcano's magma plumbing system itself. If that makes sense.
Yeah.
Um,
Yeah, I think that gets it.
There certainly can be changes, like, you know, if you have some wobble and you're changing your rotation axis a little bit too, then, you know, maybe you can have subtle effects, but really I don't see any easy to see evidence of that. It's the easiest way to put it, I suppose. Maybe some data that we found.
Well, let's go back and end with one last question about the lava lake inside Halemaʻumaʻu. Is there a reason why the west vent is less active, or a known reason at least?
No, that's a great question. That's been the big mystery for a while, is how can the caldera be spreading and lifting up while we see gas emissions going down, and gas emissions are a proxy for how much lava is coming out. So the amount of lava is going down. What's going on there, right? So
Good question.
are we building pressure in a separate unconnected area? Now we're seeing signals of it maybe refilling the rift zone a little bit, so it's resumed that pathway. Are we tapping a limited pocket? It's not clear exactly what's going on here, right? And we'll keep an eye on that. And the most curious thing about that is how the GPS signal has recently changed as well. So we'll see what that means in the future. Watch and wait. Only way to tell.
Right. Yep. All right. Well, that does it for the question aspect of this. We will be back on Friday, and I'll pass it back to you, Phil.
Yeah, mahalo, Dane. Yeah, we'll cover Mauna Loa more so on Friday, unless there's anything super new with Kīlauea, but we'll probably start flipping them back and forth now. And we'll do more Mauna Loa on Fridays and more Kīlauea on Tuesdays, and see how that goes for a little while here. And we will have a little bit more detail on all of the statistics and all the stuff from Kīlauea next week on Tuesday, as that will be the 4-month milestone of this eruption, April 20th, following the December 20th beginning of Kilauea's eruption. So in between, we'll talk about Mauna Loa, and we'll get into all of that. And until then, he's Dane DuPont, Lip Ong, aloha.